Let's investigate how a confidence level influences a confidence interval. A 50% confidence level would have a smaller interval range than a 98% confidence level, assuming all other calculation values are the same. Why is that? The confidence level directly impacts the value that we use as the critical value for calculating the error in the interval. For a 50% confidence level, our critical value separates the right tail from the center 50% of data, and for a 98% confidence level, our critical value separates the right tail from the center 98% of the data. Notice that with a higher confidence level, the critical value is further to the right as compared to a lower confidence level. That critical value increases as it moves to the right. So when we use a larger confidence level, we end up using a larger critical value. And that critical value is used in the calculation of the error that we use to build the confidence level. So with a larger confidence level, we have a larger critical value, which causes a larger error. As we see the confidence level increase, we will see the interval increase in length as well. That error calculation, the standard error factor, also includes the sample size. So the sample size is another thing that directly impacts the length of our interval. But it's not like the confidence level. When we have a large sample, we get a smaller interval. When we have a small sample, we get a larger interval. Let's take a look at why that is. The error calculation for a confidence interval involves dividing by the square root of our sample size. Because we're dividing here, we have to consider how the division of that sample size changes the quotient. So if we look at a couple of visual examples here, we have 1 divided by 2, 1 divided by 3, 1 divided by 4. As the denominator is increasing, the quotient is decreasing. So if n, the sample size, gets larger, the quotient would get smaller. So the error would get smaller, therefore it would shrink our interval. So as we see the sample size get smaller, the interval gets longer, and as we see the sample size get larger, the interval gets smaller. This is an inverse relationship. Now that we know how the sample size influences the error in a confidence interval, we can start to craft intervals with a specified amount of error and then determine what sample size we need to make that happen. So if we're trying to make an interval for a population mean, we calculate the error-bound mean using a t-critical value times sample standard deviation divided by the square root of n. I'm going to simplify that notation just a bit. I'll use e for error, t for our critical value. That will make this a little simpler. I need to solve this expression, or equation rather, for n, the sample size. I'm going to rewrite the right-hand side so that t times s appears in the numerator. Multiply both sides of the equation by the square root of n. Divide both sides of the equation by the error e. Now I have n by itself, but there's still an operation on it. I'd like to undo it, so I'll square both sides of the equation so that I have n is equal to the critical value squared times the standard deviation of my sample squared divided by the error, which should also be squared. One thing to note, we did solve this equation for n, but notice that t, the student t critical value, it actually depends on the sample size. So here, the critical value changes with the sample size. We're not totally able to determine what sample we need by using this formula. But let's take a look at the error-bound proportion. If we're making an interval to estimate the population proportion, we would calculate the error-bound proportion. So we need to solve this equation for n. I'll simplify the notation a bit. E is my error, z is the critical value, P is the probability of success, or the proportion, and Q is the complement, the probability of failure, and N, of course, is the sample size. So solving for N here, I'll start by dividing both sides by Z, then square rooting both sides of the equation, squaring, not square rooting, sorry. Then I'll have a proportion, which I can flip over and preserve the equality statement here. So I'm just flipping both sides of the equation over. Now I have N in the numerator, which makes things a little smoother. I'm going to multiply both sides of this equation by P times Q, so that finally I have P times Q times Z squared divided by E squared is equal to the sample size. We can use that equation to determine what sample size we need to force our interval to have a particular error given we know what confidence level we want to use. Let's try it. Suppose a mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers should the company survey to have a 90% confidence interval with an error that's within 3 percentage points? First, let's pull out the information in the wording of the question. We can see that we are being asked to find the sample size. How many customers? That's the same thing as saying find the sample size. We know we're going to consider a 90% confidence level, which means we're going to use a z-score of 1.645. We also know that we want our error to be within 3 percentage points. So we're going to keep the error within 3%. We're going to use 0.03 for the error. That formula that we just came up with in the last slide is telling us the sample size comes from P prime times Q prime times our critical value squared divided by our error squared. Now in this case, we don't have any information about what P prime is. We don't have any assumption, any estimate, and so we assume the worst case scenario, which is P prime is 50%, which also means Q prime is 50%. There's a 50-50 chance here of success and failure. Anytime you don't have a point estimate to start with here, you assume 50-50. So we plug in 0.5 for P prime and 0.5 for Q prime, which changes our expression to look like 1/4 times z squared over the error squared. Now we can plug in the critical value and the error that we would like to use for this study. The sample size is 1/4 times 1.645 squared divided by 0.03 squared. That comes out to be 751.7 approximately. Now notice that that number represents a sample size. So having a decimal doesn't really make sense. We can't take a sample of 751.7 people. We will always round our sample size up to the next whole number. This will guarantee that our error will be within 3 percentage points. Remember that the larger the sample size, the smaller the error. So we're going to shrink the error by increasing the sample size.